2, 1. All right, so I thought I would finish the notes today and have the worksheet due tomorrow, but we had some technology issues in first period, and I couldn't get it to connect, and finally I did, and by that time we had lost a lot of time. So we're going to finish the notes in that class tomorrow. Tomorrow is Wednesday. It's a short period, so we're only in each class for like 36 minutes. So that'll be just enough time to quiz and to finish the notes, okay, if we don't finish in class. Quiz, yeah. Yeah, and then your worksheet will be due on Thursday, okay? The quiz will be over the 3-step definition of continuity, like yesterday's warm-ups, and like example 10, D, E, and F, all right? Like yesterday's warm-up, the 3-step definition with notation, and like questions D, E, and F that we haven't done yet, okay? So the worksheet is not due tomorrow for y'all either, all right? Even if we do finish, it'll be due on Thursday. But you don't want to be going home finishing a worksheet after trick or treat on Halloween Happening Street or whatever it's called Wednesday night. Okay, so remember a horizontal asymptote. We talked about that last couple of days. It's an end behavior asymptote. It's an end behavior asymptote. It's not a discontinuity. So 2 things to clarify about a horizontal asymptote. Number 1, it is not a discontinuity, although it is an asymptote. That's actually number 2 up there. And number 2, which is really number 1 up there, because it is not a discontinuity, you can actually cross a horizontal asymptote. It's not a requirement, and not every graph will cross its horizontal asymptote, but it can happen. So I showed you these 3 examples. By the way, we did not do example 9, so we're not going to come back to it. I gave you this instead of example 9. Neither of these 3 graphs cross their horizontal asymptotes, but they all have a horizontal asymptote. In the first one, it's the same asymptote affecting the graph on both ends. In the second one, there's only one asymptote horizontally, but it's only affecting the graph on one end of the graph. And in the third one, there's actually 2 horizontal asymptotes, which is the maximum number you can have, and it's affecting the graph differently on both ends. When we talk about the end of the graph, we're talking about either one of the 2 ends, right? The left end or the right end. And remember, we evaluate those by looking at these 2 limits. Those 2 limits are the end behavior limits. And that becomes the 2 pieces of analyses that we write down when we're trying to either talk about the end behavior or discover if a function has a horizontal asymptote. Remember, the definition, though, of a horizontal asymptote is if either one of those end behavior asymptotes, either one of them or both, equal a finite y value, then by definition, we have a horizontal asymptote at y equals, that finite y value, and vice versa. Now, let me give you a quick example here that emphasizes point number 1 up here, that a graph may cross its horizontal asymptote. You can actually have in calculus, we look at this function. It's related to a trigonometric function that we'll study later in the year. You have these sinusoidal graphs that cross their x-axis infinitely many times. But here's one that crosses the x-axis, but each time it does it, it's by less and less and less and less, okay? It gets harder and harder to draw it oscillating above and below the x-axis. But if you were to zoom in way down here, it would look, every time, it would look like that, okay? In other words, it does cross the x-axis over and over and over again. But each time it crosses it, it stays closer to the x-axis. It doesn't veer as far away from it. So we would say in this case, the limit as x goes to infinity, let's call this function f of x, we would say that it equals 0, okay? Because we do know in the end where the y values are tending. They're tending towards 0. And by definition then, this would also have then a horizontal asymptote at y equals 0. How many times then would this graph cross its horizontal asymptote? Infinitely many times. That's right. So can a graph cross its horizontal asymptote? For sure. This would be a good example graphically to have in your example bag where you keep your examples of one that does, right? and it irrefutably crosses it. Okay. So anyway, not every graph will. What we're going to do on example 10 then is we're going to do three things. We're going to analyze the limit as x goes to negative infinity, the left end of the graphs. The limit as x goes to positive infinity, the right end of the graphs. And then we're going to use our information from parts 1 and 2 to answer part 3. Is there a horizontal asymptote? And if so, what's the equation? Now, how are we going to know after we complete part I and II if part III is going to have a horizontal asymptote or not? III. What will we see in one or both of our answers to I and II if I know there's going to be a horizontal asymptote on part III? Yes, you do know. I've already reviewed it today since y'all been here. The sky's the limit. Yes, y'all got that. But we need to get this too, right? Remember the definition of a horizontal asymptote. If either one of those end behavior limits ends up being a finite y value, then the function will have a horizontal asymptote at y equals that finite y value, right? So when we answer 1 and 2, if either one of those limits or both end up being a finite y value, we'll have a horizontal asymptote at that. If neither one of them ends up being a finite y value, then no horizontal asymptotes, okay? So let's go ahead and write out our work here first. Part I is going to be, hang on, smaller, write it smaller. Part I is going to be the limit as x goes to negative infinity of f of x. Part II is going to be the limit as x goes to positive infinity of f of x. And part III is going to be the question, horizontal asymptotes. Now, because we're going to be doing these three things for each of these examples, what you can do here is write it one time and copy it, and then we can just paste it on the others, because all the functions names in example 10 are F as well. So write it once, copy it. That's working smartly. All right, now the limit as x goes to negative infinity. Let's see how we can answer that. Well, what do you know about this graph of this function f of x? What does a graph as? It's a parabola opening what, up or down? It's down because the leading coefficient, -3, is negative. Now, because we want the end behavior, not the local behavior, we don't really need to find the x-intercepts. I'm just going to come down here and say, okay, I know it opens down or downward. If you kind of know what the graph looks like, you can answer the end behavior limits like crazy fast as well. Watch. What would be the limit as x goes to negative infinity? We'll hop on the graph and go out to the left. Where are the y values going? They're going down, down, down to negative infinity. So again, remember, if you write straight down, you don't need the equal sign. If you write left to right, you do. What would be another answer that's not as good, but still equivalent for a free response answer? Does not exist, right? Does not exist. I like negative infinity because remember, it tells us why. So this means as the graph goes out to the left, the y values decrease without bound. Boom. What about the limit as x goes to positive infinity? Also negative infinity, right? As you go out to the right, the y values decrease without bound, or DNE. Now, all we got to do for part III is look at those two and ask ourselves, are either one of those a finite y value? No, in fact, they are both what? Not finite, but infinite. Infinite. Infinite means infinite, right? So we'll just put none. None. So that's one way to do it. You're not always going to know what the graph looks like, though. And if you just want the end behavior, there's a much faster way, especially when you don't know what the graph looks like. Here's what you could do. If you go to any function and you identify the piece of the function that is contributing to the majority of the growth for large values of x, positive or negative, magnitude large values of x, then the function is going to go the way that one piece does. So with these three terms, which piece is going to be contributing most of the mass for huge values of x? The negative 3x squared. Why? Because it's got the, yeah, not just the exponent, the largest exponent, right? We call this right here, remember, the leading term. Because it's not in the front, but because it has the largest exponent. So if you think about like 10 billion, right? What's bigger, 10 billion to the first or 10 billion squared? 10 billion squared, okay? Now, this little trick only works for looking at the end behaviors, infinity or negative infinity. All you got to do is focus in on that leading term. Whoa, I meant highlighter, not scribble out. Focus on that leading term, okay? The other stuff that's not highlighted in green, it contributes to the function, but it's going to show up more in the local behavior, right? The x-intercepts, the y-intercepts, the local max, all that stuff. Not the end behavior, okay? So all you got to do now is plug in the type of infinity you're approaching into the leading term only, okay? Now, infinity is not a number, so you can't really plug in infinity. So let's just plug in a negative huge number and see what that gives us, okay? What is negative huge squared? What kind of huger? Positive huger, but I like huger. Positive huger, good. What's positive huger times negative 3? Negative huger. It could be the hugest, but we still need room to get bigger. So negative huger. Well, guess what negative huger is in terms of infinity? Negative infinity. Yeah. So if you get that idea of going huge, huger, we can actually plug in infinity. It's a very informal process anyway. So let's do it with the negative infinity. What's negative infinity squared? Positive infinity. What's positive infinity times negative 3? Negative infinity, right? Negative infinity. And there's your answer. Okay. Now let's do this one. What would be the limit as x goes to positive infinity? Well, let's plug in a positive infinity to the leading term only. Positive infinity squared, still positive infinity, right? What's positive infinity times negative 3? Negative infinity. Infinity times 3 is still infinity, right? Infinity squared is still infinity. Infinity minus 10 is still infinity. Infinity plus 10 is still infinity, right? So that ends up being negative infinity. And there's the quicker way to do it, okay? But it only works for end behavior where you can just use the leading terms. All right, comments on that one, questions on that one, we good? Letter B. Hey, this one is 4x cubed minus 2. Let's go ahead and do this one by the triple H method, huge, huger, okay? First thing I'm going to do is paste down my analysis tools. There we go. And now, if I want to go to negative infinity, let's just plug a negative infinity into 4x cubed. What's negative infinity cubed? Well, it's going to be infinity still, because infinity cubed is infinity, but is it positive or negative? What's a negative number cubed? Negative. So negative infinity cubed is still negative infinity. And then negative infinity times positive 4 is negative infinity. Yeah. So that's the answer right here, negative infinity, or D and E, but negative infinity is preferred. What will be the limit as x goes to positive infinity? Well, positive infinity cubed is positive infinity. Positive infinity times positive 4 is positive infinity. Do I need to put the plus sign in front of the infinity if it's positive? No. Okay. Do I need to put the negative in front of negative infinity if it's negative? Yes. Okay. Are either one of those finite? No, they're both infinite. So horizontal asymptotes, question mark? No, none. Okay. That's a quicker, faster, easier way to do it. Now, let's go ahead and do this one also by transformation and verify. We should get the same answer because this is a parent function Y'all should know. So let's review it. What is the parent function to 4x cubed minus 2? Well, just what's the equation of it? You're right. It's just x cubed, right? And x cubed is a weird squiggly, as you said. It comes in and it approaches the origin like it's going to bounce and go back down like a negative x squared, but then it goes psi, and then it turns upward like that. There's your parent function. I call this the discograph, right? It looks like John Travolta in Saturday Night Fever with his arms like that. Staying alive, staying alive. Now, what does the 4 do to this graph and any graph when it's out in front? Vertically stretches it, right? Vertical stretch by a factor of 4. It makes it steeper. What does the minus 2 do to this graph? It makes it down 2. Shifts it down 2. 1, 2, negative 2. So there's where the old origin is. And now it's a little bit steeper. I'm going to exaggerate the steepness just so we can see it. It looks something like that. All right. There's what the function f of x looks like. And now compare it. How do we do with our Triple H plugin method? Let's see. As we go out to the left, it's going down forever. That's good. As we go out to the right, it's going up forever. No horizontal asymptotes. Yeah. Perfect. So x cubed, the weird squiggly graph, your discograph, is now on your parent function list. We've talked about x, x squared, and x cubed. We've talked about 1 over x, and we've talked about the square root of x. Okay, so those are the ones you should know. All right, letter B. Step 1, paste. Don't eat it. Paste. It was kind of hard not to eat paste in elementary school, especially since they started making flavored paste. Right? Yeah. Did y'all ever buy flavored paste? Like, tastes like Oreo cookies. I'm like, tastes like strawberries. And then you're still not supposed to eat it. But it was non-toxic, so it didn't hurt you. But you were still not. Why'd they make it flavored? I don't know. Yeah. Yeah. I guess it smells different. All right. Let's go ahead and try the plug-in method here. If I want to know what the limit is as we go to negative infinity, plug in a negative infinity for x. What's negative infinity minus 5? Negative infinity, right? You owe me infinitely many dollars and then you owe me 5 more. You still practically owe me negative infinity, right? What's the square root of negative infinity? D and E. The square root of any negative number, regardless of the size, is D and E. It's imaginary. We're in the real world. So it's not in the domain. The function doesn't live out there. Does it make sense to talk about the limit out there where the graph doesn't even exist? No. So not only is the square root of a negative number non-existent, guess what the limit is? Non-existent. So that's D and E. And that's for a very specific reason, because the graph doesn't live out there. Okay. So D and E, remember, catch-all category. Let's try the limit as x goes to positive infinity. Infinity minus 5, infinity, right? If you owe me infinitely dollars and you pay me back 5, you still owe me infinity. What's the square root of infinity? Still infinity, right? You're not going to make it smaller, silly. Square root of infinity is infinity. What's infinity times 2? Infinity. Very good. Or what? Or no, not it's only positive infinity. But what's another acceptable answer here besides infinity? D and E. Now that would be a D and E that's very, very different than this D and E, yes? Which is why we prefer positive infinity. Limits can fail to exist for a lot of different reasons. Okay, now are either one of those finite? No. So horizontal asymptotes? None. None. So there's 3 in a row without any horizontal asymptotes. I guess we can conclude that no other graphs in the whole world have horizontal asymptotes, I guess. This one, by the way, you should know what this graph looks like. The parent function is radical x. The 2 makes it steeper by a factor of 2 vertically. The minus 5 moves it right 5. So now it looks like this. Okay. And you can tell what's the limit as x goes to negative infinity? Well, The graph doesn't even live to the left of 5. So when we talk about the left end behavior, we're not talking about the left end of the graph, right? We're not talking about the leftmost point of the graph. When we talk about left end behavior, we're talking about negative infinity. And then, of course, the limit as x goes to positive infinity is positive infinity. It almost looks like this one should have a horizontal asymptote because that graph is increasing at a decreasing rate. But it never tapers off towards a specific y value. It actually continues to go up, up, up forever and ever towards infinity, just not very rapidly. Oh, maybe, but these are too easy and too boring to be on the quiz, right? Yeah, I agree. Very good. I would definitely have one of these on the quiz, or if not both, 3-step definition with notation, and then one of the next 3, okay? Well, yeah, the interesting ones. Look at 10, look at 10, D, E, and F. These are different than the previous 3 because they're actually ratios, yeah? These are fractions, good. Ratios. It's a ratio of 2 polynomials. Now, here's what's cool about finding the end behavior of rational functions. All you got to do is compare how fast the numerator grows compared to how fast the denominator grows. And there's really 3 things that can happen. Either the denominator, I got stuck there. Either the denominator is going to grow faster, or the numerator is going to grow faster, or they're going to grow at effectively the same rate. That's pretty much it, right? For huge values of x plus or minus, either the bottom grows faster, the top grows faster, or they grow at the same rate. In each of those 3 cases, we get a slightly different result on the end behavior, okay? And that's what we're going to explore right now. All right, so step 1, go ahead and paste your notation there. All right, so what am I going to do? I'm going to look at how fast the numerator grows. And we can still do the same little trick of looking at its leading term. The numerator is linear, so it grows for large value of x as the leading term 3x grows, okay? The bottom is a quadratic, so for large values of x, and when I say large, I mean magnitude-wise, plus or minus infinity. It grows according to the leading term 5x squared. The plus 1 minus 2, not really helping out for infinitely large values of x, okay? But they are affecting the graph locally. Now, this question's easy. It's really a 3x to the first on the top and a 5x squared on the bottom. For large values of x, which one grows faster, top or bottom? The bottom, because it's squared, right? Now the top is still growing, but not as fast as the bottom. So I want to show you this little sequence right here. Let's list 5 fractions right above there, and let's make both the numerator and denominator grow. But let's make the numerator grow slowly, like 1, 2, 3, 4, 5. Everyone agree that that's getting bigger up there? 1, 2, 3, 4, 5, getting bigger. Let's exaggerate the denominator. Let's make it grow faster. 1, 10, 100, 1,000, 10,000, increased by a factor of 10. Because really, it doesn't matter how much faster the bottom grows than the top. If the bottom grows faster than the top, you're going to get the same result every time, okay? What's happening then to those ratios as we go from left to right? They're getting smaller, aren't they? Smaller and smaller and smaller and smaller and smaller, approaching what? Negative infinity, question mark? Positive infinity, that's not small. No, they are positive, but they're getting infinitely small, approaching 0. This goes back to the same like concentration of urine in the ocean thing, right? The concentration is getting diluter and diluter, right? It's approaching 0. Will it ever equal 0? No, because the numerator is never 0, right? But it'll get so small that it's practically 0. Well, guess what happens then to the 2 one-sided limits if the bottom's getting bigger faster than the top? They're both approaching zero. They are both approaching zero. Without a doubt. Without a doubt. Okay. Now, are either one of those two values finite? Yeah, 0 is finite. So guess what? F has a horizontal asymptote at y equals 0. One asymptote, like the graph of 1 over x, but it affects the graph on both ends, okay? Now, there's one other thing we can do here when it approaches 0. 0 is the x-axis. It's the divider between positive y values and negative y values. So I can actually figure out if it's approaching 0 from above or below the x-axis. And here's how we do that. All we have to do is plug in a representative sign for each type of infinity that we're approaching into the leading terms, okay? So if we're going to the left out towards negative infinity, plug a negative number into the leading terms, the highlighted piece. And all we're interested in is the sign. In the top, what's a negative times a positive 3? Negative, right? In the bottom, what's negative squared? Positive. Positive times positive 5 is positive. So the ratio ends up being a negative over a positive, which is a negative divided by a positive is negative, negative. So these are going to be always negative values. As you go out to the left, you're going to have negative y values. So this is going to be approaching 0 from below. Okay, and that's going to be very, very similar to up here, the graph of 1 over x. Remember, as we went out to the left, it was also approaching 0 from below. You had negative ratios, and they were actually increasing towards 0. It's going to be the same with this function. Yeah.
Can you write like the positive and negative exponent like looking thing on the 0 so that you can shove it?
It's not customary, but I would be up for like voting that, you know, if, yeah, 0 with a negative, he was asking, could you put 0 negative? I wouldn't be against that. That's not conventional though. But yeah. I mean, if all the math people met and you brought that up, I would definitely be on your side. I would say, yeah, let's do that. I like that because it's a subtle way to give that information. Yeah, very good. I'm not going to necessarily make you find this, but when we're interested in sketching the graph, that's helpful to know. Okay. And then as we go to the right, is it approaching from above or below the x-axis? Well, we already know it's going to 0. Just plug in a positive number because we're going to positive infinity into the leading terms. Positive times 3 is positive. Positive squared is positive times positive 5 is positive. Positive divided by positive is positive. So we're going to have positive y values as we go to the right. So this is approaching 0 from above. So negative, positive. I like that. I'll just leave those there. I kind of like that. Yeah. In fact, I'm going to look that up because I haven't seen that. I don't want to say it's not by command. I haven't seen that, but it's such a good idea. I'm surprised that no one as smart as you has thought of that and that it hasn't caught on yet. So let me look into that and then I'll get back with you. But yeah, I like that. All right. So anyway, that's just bonus information that we can get pretty much for no additional cost. All right. That's going to be also very similar to the graph of 1 over x. The graph of 1 over x also, as we go out to the right, approaches 0 from above. Okay. So let's summarize this. Let's summarize this. It doesn't matter if that had been 3x to the first over 5x cubed, or 3x to the first over 5x to the fourth, or 3x to the 50th over 5x to the 100th, okay? As long as the bottom has a larger degree, it's growing faster. And as long as it's growing faster, it's always going to 0, always, on both sides. The greater the degree difference, the faster it's going to 0. But is it even a race? No, because they have forever to try to get there. These types of functions actually will not cross their horizontal asymptote. They'll get closer and closer to 0, but they'll never actually reach it, okay? So here's the summary then for this type of problem, okay? When the bottom grows faster, what's the correct term for the bottom of this fraction? Denominator. Would you rather write that instead of bottom? Me neither. Good. When the bottom grows faster, comma, the end behaviors, plural, the end behaviors are 0. Okay, which means that there's a horizontal asymptote. All right. I'm not going to put at y equals 0, but you know that. The end behavior answers are the same as your y equals horizontal asymptote answers. Same thing. The limits are the analysis. All right. Anytime the bottom goes faster, anytime, it's always going to 0. All you got to do is look at the leading terms. Are these the leading terms because they're in the front? No, it's because they have the largest exponent. Okay. Questions on the first case. When the bottom goes faster, always 0. Good. Number E. First things first, let's go ahead and paste our analyses tools. All right, it's a ratio. We're going to the end behaviors only. So it simplifies the problem. We don't have to worry about factoring and doing all that domain stuff. We just identify the leading term with the correct sign. If it's not in the front, like in the numerator, make sure you grab the sign. It's +4, okay? In the bottom, the leading term is in the front. It's +3. Everything else that's not highlighted will affect the graph locally, but not on the end behavior. So which grows faster, x squared or x squared? They grow at the same rate. The only difference are their coefficients. But here's what we could say. For large x, comma, this function can be approximated by 4x squared over 3x squared. Make sure you put the squiggle sign. They won't ever be the same. Those other values that aren't highlighted, keep them from being exactly the same. But for huge values of x, those things that aren't highlighted, they become increasingly inconsequential. And it will approach the graph of 4x squared over 3x squared. Well, if I told you that that's approaching that, and you see those x squareds there, you might be tempted to do what with them? What can we do? Divide them out, right? Yeah. And if it is in fact equal to that, they will divide out and you'll end up with 4/3. So look what I just said. For really large magnitude values of x, f of x is becoming 4/3. It's becoming the horizontal line y equals 4/3. Guess then what the two end behavior limits are. 4/3, both of them. Yep. Now we're not going to look to see if it approaches 4/3 from above or below, because that's not as easy a question to ask or answer, I should say, because we're not just looking for positive and negative. We'll have to look at the actual value, but they're both approaching 4/3. Is 4/3 a finite value? Yep. So F is going to have a horizontal asymptote, at y equals 4/3. One horizontal asymptote, again, affecting the graph on both sides. Same way. Both of them are going to be that. Now, it doesn't matter if it were 4x to the 12th over 3x to the 12th, or 4x to the 100th over 3x to the 100th. As long as they're the same, it's going to be leading coefficient over leading coefficient. In fact, let's say that. When the top, which I write instead of the numerator, and the bottom grow at the same rate. And if you want to add a little note there to yourself, same exponents, same degree. I'll put that in parentheses, same degrees, comma, the end behaviors are going to be leading coefficient, and I'll abbreviate coefficient COEFF, over leading coefficient. And then, of course, you will have horizontal asymptote as well at y equals leading coefficient over leading coefficient. So there's only three cases, right? Bottom grows big, faster, grow at the same rate, top grows faster. And so far in two of the three, we've had a horizontal asymptote in two of the three. First one's always zero, never not zero. The second one's might be zero, probably not. It's going to be leading coefficient over leading coefficient. It's not always 4/3, that's for sure. All right. Super easy. And then the third one, what's the third case? Bottom grows bigger, grows at the same rate. Now the third case would be top grows faster. Yeah. Bigger, faster, I should say. So let's paste our analysis tools. There we go. Identify the leading term. In the top, it's 4x to the fifth. And the bottom, it's 6x to the fourth, question mark? Negative 6x to the fourth. Yeah, be careful to grab the sign as well. So again, you don't have to worry about the other non-highlighted stuff because they affect the graph locally. This one now is growing faster in the top because 5 is bigger than 4. So let's do that same little trick we did on part E or D, sorry. Let's go ahead and give ourselves 5 ratios. And now let's make the denominator grow modestly. 1, 2, 3, 4, 5. It's getting bigger. And now the numerator is growing faster. 1, 10, 100, 1,000, 10,000, so on and so forth. Increased by a factor of 10. What's now happening with those ratios? Very good. These are getting infinitely large, approaching infinity. Now, they could also be negative. So let's go ahead and come back in the front here and put plus or minus over those. And they'll be approaching the appropriate type of infinity. But there is not going to be a horizontal asymptote because both of the ends are going to be one or the other. So no horizontal asymptotes on part I. Now, here's what we know right away for numbers 1 and 2. If they're approaching some type of infinity, I know that the better answer to both of these is going to be some type of infinity. I don't know if it's plus infinity or minus infinity. So I'm going to highlight in front because I still need to find whether it's plus or minus. If this were a free response question, though, you could be done already by putting what there instead? D and E, right? We don't have to know if it's plus D and E or minus D and E. Okay. Now, how do you think we're going to determine if it's plus or minus? Now that we know it's some type of infinity. Graph it? Sure, that would work. That would take a long time, though. Plug it in. Yeah, we're going to do the same thing we did on part D when we were looking to see if it approached from above or below. All we got to do is plug in the sign. If we're going to negative infinity, plug a negative into the leading terms and see what the sign is, okay? Let's do that together. A negative number to the 5th power is negative still, right? And then a negative times positive 4 is negative. So the numerator is negative, remember that. And then the bottom, a negative to the 4th is positive times negative 6 makes it negative again. So now we have a negative divided by a negative, which is positive. Yeah. So this one is going to positive infinity. And although I don't need the plus sign in front, I feel like leaving it there this time, right? Positive infinity. And then if you plug in a positive number for part II, you get positive to the 5th is positive times positive 4 is positive. So the top is positive. And the bottom positive to the 4th is positive times negative 6 is negative. A positive divided by a negative is negative. Yeah. So they have opposite end behaviors. This one comes in the top and goes out the bottom. Sweet. No horizontal asymptotes. So here's the summary on that one then. When the top grows faster, comma, the end behaviors are either positive infinity or negative infinity, and there's no horizontal asymptotes because neither one of those are finite. And of course, you get the sign by plugging in. So those are the three cases. And if I just work more problems, the numbers would just be different, okay? It would be one thing for me to give you those three rules, which are the summaries, and then say try them out. But we did that after we discovered why, right? So now that you know the why and you know why that rule exists, then it makes the how a lot easier. Okay. Oh yeah, that makes perfect sense that it would be that answer. The summary just kind of helps you remember it. All right. Okay. Comments or questions on that? Quiz tomorrow over continuity, 3-step definition, and a couple of end behavior limits. Find horizontal asymptotes with the analysis, right? The analysis are the two one-sided limits, negative infinity, infinity. That's the end behavior of the graph. All right. Example 11, putting it all together. There's a question like this on the worksheet. When you turn your worksheet in on Thursday, it shouldn't just be copying the key, because there are literally infinitely many different ways you can do these types of problems, okay? What I'm doing is I'm giving you just a couple of basic criteria that your graph need to follow. And then everything else that's not included here can be dealer's choice. So we want to graph a function on the interval from -5 to infinity that has the following criteria. All right. So let's just go ahead. I'll pick blue here for my graph. We have to go all the way out to -5. So -1, -2, -3, -4. There's -5. And now let's just go from left to right. The first piece of information says the limit from the left of -3 has to equal -2, and that also has to equal the function value. Okay, so that means the road coming in equals the bridge, and they have to meet up at -3, -2. So let me come over here to -3, and then -2 would be right here. And I'm going to put a solid dot because it said that's the function value. And now the limit from the left has to go into that spot. Now, you have some choices. Do you want it to come in from the top? Do you want it to come in horizontally, or do you want it to come in from the bottom? It's entirely up to you. I'm just going to make mine come in from the bottom. Now, I'm just going to draw a little piece. I don't want to draw a huge piece because I don't want it to overlap any of the other criteria. That's enough to tell me that the limit from the left equals the function value at -3. Yes? That's it. So just put a little piece down. All right, that takes care of that. The next piece says the limit from the right of -3 equals infinity. Well, guess what has to live there at -3 to help guide my values up to infinity? A vertical asymptote. Yeah, so let me draw that first. Okay, and you could draw it all the way north to south, but I'm just going to leave it there. Now, I'm going to draw mine just coming in like this. All right, just like that. You could actually have it coming from below the x-axis if you wanted to. I'm just going to have mine coming in from above the x-axis. And just a little tail on it, just to know that it's coming in from the right. All right, the next piece, it says that the limit as x goes to 0 in general, that would be from the left and the right, has to equal the function value. So the function value at 0 has to be 0. So it has to pass through the origin. Now you have some options here. Do you want it to cross through like this? Do you want it to cross through like that? Do you want it to bounce from below? Or do you want it to bounce from above? It has to be continuous there, right? That's the last one I drew, so I'll just leave that one, okay? The general limit exists and is 0, so that means the limit from the left equals the limit from the right, and they both equal the function value. So that means it's continuous there, passes through the origin. All right, the next piece, the limit as x goes to 3 from the left is 4. So now I need to come over here to 1, 2, 3. And the limit is 4. 1, 2, 3, 4. There's 4. I'm going to put an open circle there because it didn't say anything about the function value. And I'm going to have it coming in from the bottom. Okay. So something like that. Something like that. The limit from the right of 3 is 1. So there's 1. I'm going to move this guy down here. And there's an open circle. And what the heck, I'll have it look like that. And then it says f of 3 is -1. So that's going to be right here. And that's the function value. So that takes care of those two pieces at 3. And now I just need the last piece, which is the right end behavior, right? As I approach positive infinity, the graph approaches 2. Well, what's going to live there graphically that's going to help guide my y values to 2 as I go out to the right? Horizontal asymptote. So you could draw it all the way across, but I'm just going to draw it right here. Here's y equals 2. I'm going to have it come in from above, right? And then all you got to do is fill in the blanks. I'll use green here. So you could do that, you know, fill in the blanks. And I'll have it cross the horizontal asymptote. And there it is. Label it as F and you're done. Everything that's in blue has to be there. Everything in green, you're just kind of connecting the dots, making it up as you go along. Make sure it passes the vertical line test. All right, tomorrow we'll end with the summary after the quiz. That's all we'll do tomorrow. Quiz, grade it, finish the notes. We only have like 36 minutes. Have a good rest of the day. Au revoir.